Okay, welcome, people of Earth, to day 16 of Advent of Code. Uh, we started a little early tonight because I had a lot of thoughts about day 15. I actually posted two videos for day 15. One that I did at the time the problem came out, and then I stewed on my solution. I was very unhappy with how day 15 went, so I did it again the following morning, and I recorded that and posted that as well. If you want to watch that. But anyway, if you're interested just in day 16, then skip ahead, 11 minutes, and we'll get right to it. But looking back on day 15, the big problem was I saw this and it was immediately obvious that it was just a shortest path problem, and I think the big thing there is I was so focused on there was an obvious solution to this problem that I just couldn't think around that obvious solution. So I kept kind of coming back to this general purpose, just do a shortest path thing. But the trouble is, a true shortest path algorithm is really hard. And I don't mean difficult. I mean, it's not appropriate for a programming contest. It requires, if you're going to do it correctly, it requires powerful data structures, and those aren't the things that we're doing as part of this event. And I knew that this was not the right solution. I knew that it would work, but I also knew this was not the right thing to do, and so the entire time I was working on this, I was just utterly distracted by knowing that I was going about this the wrong way, that there was another way to do it, and I could never really focus on the task at hand, and it went badly. And and I felt lousy when it was over, and I stewed about it until I went to bed, and yeah. Anyway, I mean, in terms of the solution we implemented at the time, I was kind of copying from Wikipedia, and I wasn't reading very carefully, and I mean, it's part of, doing something when you're on the clock and you have a camera on you is probably a little harder, but I really think the essential problem is my heart just wasn't in it. I spent the whole time thinking that I shouldn't be doing that. And when you hate what you're doing, you're not going to do it well. That's just a thing. And similarly, some of the debugging I did was clearly just displacement. I wanted to keep my fingers going, and I kind of didn't want to engage my brain. And that happens in real life as well. Plenty of times, people do debugging. They're doing it to kind of avoid sitting back and thinking things through. That's not to say that mindless debugging isn't sometimes useful and necessary, but I think you have to be aware that it can very easily turn into a displacement activity. The same as gathering performance data and so forth. That's a crucial part of improving your performance, but at a certain point, engineers can just get caught up in collecting data for collecting data's sake, right? Okay, so beyond what I actually implemented, because at the end I pulled in my hundreds of lines of priority queue of a Fibonacci heap implementation and applied that to the problem, but I'm also upset that I didn't think through any of the better ways to optimize. The right thing to do, when I realized, I'm doing an algorithm that's going to need a Fibonacci heap. What I should have done is written some data structure that had the interface of a Fibonacci heap. Mainly, you can push and pop, but also you can update a key, mainly just decreasing a key that's already in the heap, right? And you can write a data structure that works like that, but that has different complexity bounds. And then once you have that implemented and is running slowly, you can figure out how you can get it to run faster for your particular data. And as soon as I started thinking, I came up with literally a dozen different types of data structures. Simple, I think the hip term for them is hybrid data structures, right? And something like, well, you need this heap, but actually there aren't going to be many things in it. So let's just use an array Like our simple brute force solution for the first part was really just use an array, or maybe we're using a set or something. And then when we need to find the minimum, just scan every element and find the minimum, right? And that would brute force, and you can provide an implementation that would do that. But also, I realized the number of the weights that we were putting into this priority queue were the lengths of the paths. And the lengths of the paths were never more than 500 for the first part, and never more than, 2,500 or 5,000 or something? 5,000 for the second part. Knowing that that's the case, you can actually create an array for every distinct distance, right? And then you have a continuous block of memory, which is pretty quick to scan, and and it's of a bounded size and so forth. But then, to turn it into a hybrid data structure, it's actually the case that when you're doing Dijkstra's algorithm and, you have a fringe of nodes that you're about to explore, everything on that fringe is going to have about the same weight because they're all adjacent to as far as you've gotten. So, and in fact, I think in this case that everything on that fringe, all the weights are going to be within 10 of each other. So if you use this big array where you have a bucket for every possible weight, but then you have, and the main operation that we might be doing is trying to find, the first bucket that has something in it. Well, you can actually keep track of what that first bucket is. And all the buckets that are full are going to be within 10 of that. So you can actually set up a very simple data structure where all you have to do is probe an array at most 10 deep, and that is like blindingly fast on hardware. And, the theme that we'll keep coming back to, scanning arrays of a dozen elements or 100 elements is so much faster than traversing some complicated tree data structure like a Fibonacci heap that in a huge number of cases, that kind of dumb data structure that doesn't get you these asymptotic bounds in the general case are going to be a much better choice if you actually care about performance. So, anyway, how far have we gotten here? So there are data structures I could have used, even if we said we were going to apply Dijkstra's algorithm. There are better data structures we could have used than a Fibonacci heap that don't require hundreds of lines of code, very straightforward, and that we could optimize piecemeal, see what's going slow and make that go faster. And I didn't even do that. And I'm kicking myself because that's supposed to be the kind of stuff that I'm good at. But anyway, and there are a few notes. We actually had the solution at one point, but for one bug. But then we went and we re-implemented it twice before we realized that the first implementation was good enough. It just had a bug in it and so forth. But anyway, if you watch the second video, you'll see or realize that there is a much more straightforward way to do this. You don't need to do a general shortest path algorithm. You can just do a breadth first search if you transform the input data into a graph with edges of equal weight. And the intuition behind that is that every node of this digit array can be treated as a stack of nodes. And the top node in a stack is connected to the bottom node of all the adjacent stacks. And what that means is that, because you have this, numbers up to 9, when you enter a node, you then have to progress up the stack 9 steps, a distance of 9, before you go on to the next one. And this sounds like kind of a weird complication, but what it means is that all your edges between both the neighbors and the stack of nodes now have a weight of 1. And that means all you have to do is search out one node at a time. And that's a very simple algorithm. Doesn't require any complicated data structures. And that, as a rule of thumb, that is the most complicated algorithm that is ever required for advent of code. That's because I've done all of the advent of code things, and I have seen people use, A* search and everything plenty of times. It is never necessary. And it wasn't necessary yesterday, which is why I was kicking myself because I knew it wasn't necessary. So don't watch the live video they recorded. Go and watch yesterday's second video. And that's a much more sensible way to do it. I still did kind of screw up on, just as an added thing, I decided to try a virtual grid, and I screwed that up in a couple of ways, so it took an extra 10 minutes, but, whatever, that's kind of what this is for. But it should be noted that, because we got the original solution with a Fibonacci heap, and then we built this much simpler solution that just did breadth first search. The breadth first search approach was like at least 5 or 10 times faster than the Fibonacci heap, because complicated data structures are slow as a rule. That's just how the game is played. So anyway, so those are my reflections on a day 15 that I consider quite educational. That's what I genuinely enjoy about doing this event. I've talked about going through the entire life cycle of a product. Usually that takes at least 6 months and often a couple of years in your career. But doing something wrong, realizing that your architecture is broken, and then rebuilding it from scratch, that's great experience that engineers should go through a lot more than they do. And in fact, most engineers in the tech industry, they work on a project for a couple of years and move on and never see the legacy of what they built, and never recognize like the huge architectural mistakes that they made. Most people never see their major mistakes. And so it's very good experience to like confront, ooh, I did this totally wrongly, I need to start over from scratch. And I don't mean like, you get a little way through and realize you start over from scratch. You build an entire system that actually works, that actually solves the problem. And then you realize, you know what, there was a much simpler way to build this. That is one of the most undervalued experiences in the industry, in my opinion. People don't think that's worth doing. But anyway, so now we're going to start on day 16, and maybe we'll try to apply some of this wisdom we have gained from our previous days. Let's see. Well, let's just see what this is. Our internet seems slow today. What? That's not what I wanted. Where's my puzzle input? Well, okay, it's just a big line, isn't it? Whoa. Whoops. I don't know what's going on with you. Really? You know what? This is just hexadecimal, isn't it? What did it copy that's, let's see if we can paste in the BB edit as a constant. Yeah, okay. I don't know what's going on with my terminal today. But anyway, so we have hexadecimal input. Fine. I know what hexadecimal is. You don't need to explain it to me. Well, so we really do need to turn it into binary digits, I guess, right? So what should we do? So, I mean, the idea here is we're turning it into a string. Let's just see, actually. But if we do that, then we're going to have to, let's just make sure this syntax works before we, oh, yeah. Okay. Zero. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. D, C, B, A. I mean, there's probably, you can actually do math on the ASCII and figure this out, but I kind of suspect that it would take me longer to get that code right than just to do this dumb repetitive code that I know I'm going to do correctly. So I'd like everyone to be impressed that I am doing binary from memory. So except I forgot that there are 4 digits in hexadecimal, so the whole thing about me being smart at that point has been slightly undermined. But now I can just add the ones. Was that foresight? It's a kind of foresight. I can't do binary backwards, though. I'm not that smart, so. Okay, so I think we have our binary string. Padded with leading zeros. Okay. This is all fussy. Okay, version type. Yeah. Variable instruction lengths are a thing the industry doesn't really do much anymore, but okay. Parse. So let's packet this is going to be super annoying, isn't it? So decode the structure. What do you get if you add up the version numbers in all the packet? We'll just hard code that would read the packet will just be about parsing right now and won't actually return us anything, and we'll just add some code to add all the version numbers. Right? Okay, so what is the structure? Begin with a standard header. Equals, come on, what is it called? D? Slice from pause to pause plus 3. Okay. Oh no. Remember how I said I was good at binary? So much for that. Prefixed. Pause. 1. Plus equals 5. And then plus equals. You know what? Let's actually do the loop the right way around. Is that how it works in Swift? I very seldom use do loops, but pause -5 because we've already incremented by 5. Okay. Every other type operator. Okay. That's just kind of my general thing for switches. Actually, I guess we do all the operators the same way. So now we need to read our subpackets. Okay. This is and now, ooh, nope. So now we need to write our from binary. Come on. Okay. Is reverse a function? I think it's a function. No, I don't need to reverse it, do I? Don't know what I was thinking there. Okay. So we're not calling read packet, so no danger of that. So let's just see how we're doing on compilation as usual. Where's D? What do you mean? What do you mean you can't find D? Oh, that was the previous one. Do while, repeat while. That's, I knew Swift had done something a little funky. Where's the, here we go. Subsequence. You know what? Let's do what we're supposed to do and say this is a. Is that a thing? Can we do that? Oh no. We could make it a template thing, but let's actually, because yeah. No, we're getting int. Yeah, here we go. And our read packets. Length. Cannot find link on line 76. Yeah, and we're done. Version, yeah, okay, I get that we're not using that right now. And that should be what? 8, 9, 10. 10. Yeah, okay. Yeah. Okay, so let's assume our firm binary is working. So now let's try reading doesn't return anything, so let's just P. Let's try reading our first packet and seeing nothing bad happened. So that's interesting. And what are we trying to do? We might as well just lay down the code. Decode the structure. What do you get if you add up all the version numbers and all the packets? So come on. From binary of version, right? But we just read one packet. So let's print d count p. Okay, so while p is less than. Ooh. Yeah. Assertion on 73. Oh. So 15, 1 slice. If this is zeros, okay. So where does it end? Hang on. The bits transmission contains a single packet. These are not a single packet. So I guess we're doing something wrong here if we're doing this while loop, right? D count P. Oh, wait, we might have gotten it the first time. So there are 52, 49. Yeah, so let's see if this is the right answer. Yeah, okay, good. Oh, and we get a chance to make the leaderboard. Let's do better. Some of the values, okay. Okay, so reading a packet returns an integer. Oh no. Hold on. No. Okay. Okay. This isn't the right code structure, but we're in a hurry here, aren't we? So var subs. that's the if, so we're still on the default. So we're gonna switch on the same thing again. Switch type again. So return. Value. Maximum. The value is 1. This could have been a cut and paste, but okay. Okay. How'd we do? Nope. Hold on. The first one. Oh, what? We didn't do the right thing here. Right. Return from these, and then we come on. Maybe. Hey! Rank 110! We almost made the leaderboard! I was not very didactic in this because but we were so close! So, anyway. Clearly not a super algorithmically interesting problem, just a matter of how quickly you could follow directions and whether you could code it without making any mistakes. And so, hey, so that was fun. Half an hour plus, like 15 minutes of talking at the beginning. So anyway, I will see you tomorrow for day 17 of Advent of Code. See you then.